He is actually an early bird. We have to just follow him so that we will get the prey early. We got great support and motivation from him. On behalf of all of you, I welcome you, Father, to this function. Today's chief guest is Dr. N. Shaji. I know him over the years. He is a professor at Maharajas College, Ernakulam. He is a well-known teacher who can teach subject at grassroots level. He is an apt person for starting such a bridge program. He is a very simple and humble person, at the same time highly effective teacher. He is heading the Shastra Sahitya Parishad of our state. I am very happy and honored to have you for this function. I welcome him to this function, or on behalf of all of you, I welcome you, sir, to this function.
Thank you.
I appreciate the great effort by the coordinator Navya Miss and the joint coordinator Andros Miss for initiating these programs and coordinating it in the best way for the department. Then I invite all the other participants, our guest teachers and students from other institutions, and from our own students and my colleagues to this function. Once again, I welcome you all. Thank you.
Thank you, sir. We also extend our warm welcome to our HOD, Dr. C.B. Matthew, to today's session. Welcome, sir. For the presidential utters. Please, sir.
Yeah,
Welcome.
good afternoon, everyone. Thank you. I was actually engaged in a meeting of college itself, but engaged totally. I could only see you, I couldn't hear fully, but I could make out Dr. Sibi was welcoming us all, and also Shaji sir and welcome Jian Mansai. So I also welcome Professor Shaji and all others. So this is, if I understand this Initium is meant to be an initiation for the PG students, right? Am I right?
Yes, Father. Yes, Father.
So thank you, PG students. Good to see you. I hear that every day there is the group is very volatile. Every day, or highly mobile. Every day somebody is missing and somebody new faces coming up. That's what I heard. But then that's not very happy kind of a thing for a group to be. And usually doesn't give good health to the group. And it will affect our learning also. But what to do? This is the COVID-related circumstances and we have to put up with that. But all the same, I'm happy that you are in PG, postgraduate studies. That is the highest level of learning and the normal procedure which will happen in any country for the time being. And it's also again not normal, it's not abnormal, but it's super normal or supranormal. Because normally our students cannot attain up to PG level. In India, it is only about 36% of students of college going age are able to access higher education. That too, higher education doesn't mean that PG. When it comes to PG, it will be again 10% of what is usually in the UG. That means if there are 50 students, we have 10 students in, 5 students or 100 students, we have 10 students. Or 10 to 15 students, let us say, in PG. That's the usual proportion, and that implies that you are a very privileged group. So first of all, I think ab initium, we should feel grateful. Grateful for the unforeseen and countable kind of blessings we're getting to be in a place like this, to be in a situation like this where we can learn higher things, things of higher order. So, and gratefulness should come in the form of two things. One is that we are responsible regarding the great opportunity we are getting. And because there are many others who are willing to, interested, but are not able to get to this. And that means we have to make use of this opportunity without fail properly. And do not leave a seat vacant. And sometimes some people will go midway, and that means that seat is for nobody. It's almost injustice in depriving somebody of an opportunity. And we also get tired sometimes when they are not able to persevere. So this again a high level of responsibility. So when we take it up, we should also feel that we are taking up a great responsibility, and we owe it to the nation and to many others that we do it fully well, commit ourselves to learning throughout the 2 years and even after that. So that is number one. Number two, I feel it should also the gratefulness should also extend to another aspect of life, that we are willing to apply our learning to real life situation. So it's not only scoring high marks, but then are we able to translate something or put something of what we learn into practice? So this is a skill we should deliberately acquire. Usually it is not acquired. Usually it will remain at the head level, maybe at the lab level you do something, but again when it comes to practically doing something in day-to-day situation, we are not able to do that. We are not able to explain the phenomenon around us. Why? What is the physics behind it? So are we able to apply our knowledge in such a way that we can analyze things happening around us, happening in us, the physics of human life, the physics of things around us, physics of plant life. So we become able to understand the intricacies of life. That's one thing we should have, and also to do certain things, like simple things as to prepare a radio, to tie a fuse. Nowadays, it is not required. Earlier, we had to tie a fuse. The fuse used to work, and then the connection used to get disconnected, and then we had to do that again. But nowadays, it is not required. But if it is required, are you able to do that? Or some such activities which is related to physics, which have come to practical life, can you identify and make people know about it? So last year, or last to last year, under the guidance of Dr. Matthew, a beautiful work was being done. We used to go to smaller communities and tell them how can we manage electricity properly, the energy through what we get through KCB. How can we optimize that? So this was a very practical kind of a thing, and people liked it, and they were very grateful for that. So these are things which you should know and which you can do and reach out to the public. And lastly, I told two things now. One is commitment to learning, second is applying learning, and third is a higher level of learning. Any guess? I'm sure that nobody will guess it. Most likely, I'm pessimistic about it. Nobody might be able to guess the third thing. Anyone, any volunteer to guess what is the third thing I'm trying to tell about learning? One is commitment to learning, learn well. Second is applying learning, and third is what is producing knowledge. Learning to produce knowledge. So this is a challenge when we should have when we are at higher education. Higher education is marked or is distinguishable from the rest of the education by this characteristic, that it is not only acquisition of knowledge, it is not only dissemination of knowledge, it is also into the production of knowledge and the methodologies for that. So that is what we call research. And everyone has to do that in a very serious manner. I think we should give utmost importance alongside acquisition of knowledge towards doing a research project as a PG student. Find something new, do something new, familiarize something with the methodology by which you can create new things or systematically analyze things. So this is a beautiful thing. And my challenge is that as PG students, at the end of the PG, you should have a proper research done and a paper published in the connection. This is a challenge, and you will be rewarded if you are able to publish in a recognizable journal your PG research. You will be rewarded, and you will not regret it. You will have a special reward from the principal's office. So this is my promise, and I'm very glad that you are all here. And I wish you the very best and enjoy learning and enjoy with the curiosity of a child as to how to discover the secrets of life around us. Too many things are there, and you are privileged to know them, and you are bound to learn them and let others know. Tell your younger brothers and sisters, or your parents, your family, your neighbors. This is why it is happening. That is the ability of favor. I've spoken a bit too much. I am very glad that you have invited me also. I wish the gathering and the program and the year and all the students the very best. May the Sacred Heart of Jesus bless us all. Thank you.
Thank you, Father. Thank you for inspiring words. As Father told, everything we see around is energy, and the intelligence is in channelizing them. Now, our dear Navya ma'am, who is always mindful about her students and is consistent in organizing things that are needed for them to shape their thoughts. Now, Navya ma'am, coordinator, shall introduce to us the speaker for the day. Welcome, ma'am.
A very warm welcome, good afternoon to all. It is a great pleasure for me to introduce my professor, Dr. N. Shadi, to this Initium series. The Initium series is designed to inculcate an attitude of inquiry in the aspirants of physics, and Dr. N. Shadi is a very suitable person to begin this series. Presently, Dr. N. Shadi is working as an adjunct faculty of Department of Physics, CUSAT. He has retired as the principal of T.M. Jacob Memorial Government College, Manimalakkunna. He took MSc from CUSAT and PhD from Institute of Mathematical Science, Chennai. He was the student of the well-known Indian theoretical physicist Dr. E.C.G. Sudarshanan. He had guided many projects and research works. His fields of interest include classical mechanics, quantum information theory, quantum mechanics, and quantum field theory. He has a teaching and research experience of more than 25 years and has received many awards for his contributions. Without extending, I request Dr. N. Shadi to deliver his lecture, An Introduction to the Foundations of Classical Mechanics, as an inaugural lecture of the Initium series. I will place that.
Thank you, Navya. Can you hear me properly?
Yes, sir.
Yes.
Can hear it.
Okay, then shall I start? Without much introduction, I will directly enter the topic that I am given. This is going to be an introduction to the foundations of classical mechanics. Okay, so classical mechanics is something uh, that you have learned from school days, but there are much more to learn in classical mechanics. And when you discuss the foundations of classical mechanics, you are actually learning the foundation of physics and to some extent the science itself. So let me begin with a presentation. You can stop me at any time, ask questions. So I'll be following the historical route. So let me open a presentation. Can you see the screen that I have shared?
Yeah.
Okay. This is just the title, An Introduction to the Foundations of Classical Mechanics. So where should you start from? Some people start from the Greek philosophers like Plato, Aristotle, and people like them. Uh, See, people used to wonder about our universe long back. If you look around from your windows, you will see many kinds of movements. You will see uh, leaves fluttering or a wind blowing, and you will see the sun rising in the east, setting, and you see the motions of planets. You'll see river flowing and things like that. But looking at these things, it's not obvious that you can write down mathematical equations for this. So you can even develop some theory. That's not at all obvious. So people like Aristotle, they had their own pet theories of how the universe works, and much of it now we realize that is wrong. But we should appreciate them in the fact that they used to observe things and wonder about this and try to make certain rules or laws of nature. One of the observations that Archimedes made and make some rules. But Archimedes, people like Aristotle, they had rules like this. For example, if you look around and see motions, they divided into two different kinds of motions. One is natural motion, and the other was forced motions. For example, you look at the sky and you will see things going around the Earth. You see sun going around and Earth, moon going around Earth. That time, that was the picture. That Earth is fixed, and these planets move around. And their expression was simple. They said that these all go in circles, and circles are the most perfect geometrical object. And if something moves in a circle, you don't have to give any particular expression for it because it is natural for bodies to move in circular orbits because that's the most perfect geometrical shape. Then what about the other things? They said heavy things falling down or things with the low density going up. These are all natural motions. So all these things are called natural motions. Right? The things falling down, heavy things falling down, light things going up. That is for terrestrial objects. For heavenly objects, a circle is the trajectory of natural motion. And other things like you pulling a cart or pushing something, these are all caused by some forces, and these are called forced motions. And this lasted for a long time, and people they thought that if you want to move something, you have to apply force. If you apply more force, it will move with a larger speed. But many of these ideas later changed, and the whole picture of the universe was changed by a person named Copernicus, followed by Tycho Brahe, Kepler, etc. So this is a timeline. So I will start with Copernicus, who actually changed the way we look at the universe. Then Tycho Brahe was a great observer, and then Kepler, then Galileo Galilei. All these names you usually associate with astronomy. So you may wonder why I am talking about these astronomers. There's a reason for it. If you look at things in Earth, things on Earth, things moving on Earth, it would have been nearly impossible to make simple laws of physics. So astronomy helped a lot in formulating these laws. There is one reason. Think of Newton's law, for example. Newton's law says that Newton's first law says that if something is at rest, it will continue at rest. And if there's no force, something moving in a straight line will continue to move in a straight line with the uniform speed. But if you look around, you never see something that is moving with the uniform speed without any force acting on it. Basically, because there's always friction. So if you look at the sky, these planets move around for a long time, for billions of years, and basically because there's no friction, so conditions are ideal there. So astronomy helped a lot in formulating classical mechanics. So I will go through the historical route, and after these astronomers, I will discuss the work of Newton, Euler, D'Alembert, Lagrange, Hamilton, etc. So this is a painting of Nicholas Copernicus. What did he do, which we now consider revolutionary? Before Copernicus, there was this Ptolemy's model of the universe, in which Earth was considered as the center of the universe, and planets like Jupiter, Saturn were going around Earth. Even Sun and Moon were considered planets. And Copernicus formulated a theory in which he said that Earth is the center. That's called a geocentric model of the universe. And he thought that if you assume that, heliocentric theory, if you assume that Earth, Sun is the center, and Earth is just a planet, you can explain the motions of planets and apparent positions very easily. And that time it was revolutionary because the thought was that Sun is at the center. So Copernicus in the beginning was very reluctant to publish his work, but when he was very old and about to die, he allowed it to be published. And for a few decades, this did not make any ripple. ഇത് വലിയ പ്രശ്നമൊന്നും ആദ്യകാലത്ത് ഉണ്ടാക്കിയില്ല. പക്ഷെ പിന്നീട് ഗലീലിയോ പോലുള്ളവര് കോപ്പർനിക്കസിന്റെ മോഡല് പോപ്പുലറൈസ് ചെയ്യാൻ നോക്കിയപ്പോഴാണ് കുറച്ച് പ്രശ്നങ്ങൾ വന്നത്. Then Copernicus book was actually banned. Then let me talk about Tycho Brahe. He also played a very important role in the development of mechanics, a very indirect role. ആയിരുന്നു Tycho Brahe. നിങ്ങൾ കേട്ടിട്ടുണ്ടാവും ചിലപ്പോൾ. Tycho Brahe was a great astronomer, very good observer of the heavens. He had the fortune of having a big observatory. What you see in the slide is Tycho Brahe's observatory, and there are a lot of people employed there. This was before the days of telescope. So there is a limit to the resolution with which you can make observations, and Tycho Brahe's observatory reached that limit. So it was definitely the best observatory people had before the invention of telescope. And he took this data with great attention to the details, and was considered very accurate. And it was the accurate data of Tycho Brahe which helped Kepler and others to formulate the laws of mechanics. This is Johannes Kepler. Kepler is known for Kepler's laws of planetary orbits. And Kepler had this great fortune of getting all of Tycho Brahe's data to analyze. So there's a lot of data acquired over several years. And actually Kepler worked on this data for about 16 years, not just a few days or months. He spent several years, and he formulated some laws. Before formulating these laws, he tried many other models for the motion of heavenly bodies, So he realized a few things. One is that Sun is the center of the universe. Earth and other planets move around the Sun. Then he realized that these orbits are not circles, but these are ellipses. That is known as the first law. This is the first law. And the second law was that what is called the law of equal areas. In equal times, the radius vector will sweep equal areas. That is another observation by Kepler. And the third law, which says that basically P square and A cube are proportional, where A is a semi-major axis and T is the period of a planet. This was very crucial for people like Newton to formulate his law. Now, I should mention the name of Galileo. Galileo was one of the persons to formulate Newton's first law in a slightly different form. So Newton's first law was known before Newton. Newton did not call it Newton's first law. It's we who came late called it that way. Newton used the ideas of all the people who lived before him. He used observations and created ideas of people like Galileo, Tycho Brahe, Kepler, Descartes, and all such persons. So this is a simple experiment that led to first law. See, for example, consider inclined plane. You have one you have a pair of inclined planes. You have to start with a ball that is rolling downwards. After it reaches the lowest point, it will roll up. ഞാൻ പറയുന്നത് കേൾക്കാൻ പറ്റുന്നുണ്ടല്ലോ അല്ലേ നവ്യ? Is it okay?
കേൾക്കുന്നുണ്ട്.
കേൾക്കാം സർ, കേൾക്കാം കേൾക്കാം സർ.
ക്ലിയർ ആണല്ലോ അല്ലേ?
അതെ അതെ സാറേ, ക്ലിയർ ആണ്.
കേൾക്കുന്നില്ലാത്തതുകൊണ്ട് എനിക്ക് സംശയം വന്നിട്ട് ചോദിച്ചതാണ്.
ഇല്ല ഇല്ല, കേൾക്കാം, നന്നായിട്ട് കേൾക്കാം സർ.
Okay. So it will roll down here and then will roll up. It will not go to the same height, it will go to a lower height. But then Galileo realized that it is probably because of friction. So he polished the ball and the inclined plane and did the experiment again. Then it went almost at the same height. Then he made a guess that friction ഒട്ടും ഇല്ലാതാക്കാൻ പറ്റുമായിരുന്നെങ്കിൽ അതേ ഹൈറ്റ് തന്നെ എത്തുമായിരുന്നു എന്ന് ഗലീലിയോ ഗസ് ചെയ്തു. So this is the first case. So this rolls down here and then goes up to the same height. Second case, the first inclined plane മാറ്റുന്നില്ല, but second inclined plane is brought down. The angle is reduced. The theta is reduced. So to reach the same height, it will go further. It will travel more distance until it reaches the same height. Now he took a extreme step. You keep reducing the theta and consider a case where this is almost horizontal. Then this ball will keep rolling, so as to reach the same height. So if you just look at this motion, it is as if it is moving horizontally indefinitely. Actually, if you do the experiment, it will stop after some time because of friction. And Galileo, with this careful argument, said that if you could reduce friction to zero, it would go on and on forever. This is somewhat like Newton's first law. There is a small difference. Galileo considered the surface to be horizontal, that is parallel to the Earth's surface, not just necessarily straight line. So if you consider the Earth as a big circle, with a circular surface or a spherical surface, it will follow that. Galileo tried to use the same argument to describe the motion of, say, moon, for example. He said that the moon goes in a horizontal condition, that it will keep the same distance from the Earth center. So his idea of horizontal means you keep the distance from Earth to be fixed. So this was Galileo's idea of law. Then something more. This is about Galilean relativity. I have given the title Galilean relativity. Let me explain it. This is an original idea of Galileo, very interesting idea. He said that think of a ship, big ship, moving at some uniform speed. And if you are inside the ship, you will not realize that it is moving. So if you drop something, it will drop directly downwards. If you drop something from the mast, also it will fall directly towards the center. My drawing is not perfect, but he said it will, if you drop something from here, it will reach this. So you can have, say, birds moving in an aquarium, or some butterflies flying, and they will feel as if the ship is not moving. This, if it is moving at the uniform speed, this is called Galilean relativity. If you have a frame of reference which is moving with uniform speed, the laws of physics will be safe. You will not feel it, assuming thinking that it is a uniform speed. So it also means that, for example, if you have keep something here in this frame of reference, it is at rest. But you imagine that you are looking from outside the ship, from the seashore, then this will be moving with the uniform speed. So when you say whether something is moving with uniform speed, or you say that it is at rest, it's just a question of frames of reference. So this was one important idea of Galileo, and you will realize that all of Newton's laws are invariant under this transformation. That's whether you have a frame of reference that is at rest, or you have a frame of reference which is moving with the uniform speed. Newton's equations will be same. That's going to be true for all laws of physics that we will realize later. So this idea was that of Galileo. This was a kind of achievement, a big step at that time. Let me go to next slide. This is astronomical observations of Galileo. These are all drawings made by Galileo in the year 1610. 1610. These drawings were done in the year 1610. I think this was done in January. The dates are given here, 10, 11, 12, etc. And he was actually observing Jupiter with his telescopes. Galileo was not the first person to make telescopes, but there were other people who made telescopes, and Galileo heard about it and figured out how it works, and he actually constructed telescopes on his own, and he improved them. And when he looked at Jupiter, he found something astonishing. There were small little stars around them. After a few days observations, he realized that these are not stars. They are moving with Jupiter. They're actually moons of Jupiter, or satellites of Jupiter. Now these are known as Galilean moons. First he observed 2, then 3, then 4, and these are now known by the names Ganymede, Callisto, Io, and Europa. Huge satellites. There are several other satellites, but these are small. And observing these for a few days, he realized that Jupiter is a center for, at least for the motion of these satellites. So he could actually show that Earth is not the center of everything, at least. So that time there was a lot of argument whether Earth is the center of the universe or the Sun is the center of the universe. So this was a strong point there, that Earth is definitely not the center for everything. So he found another center, and this actually led to the his observations of planets like Venus and Mercury. They all led to the hypothesis that Sun is the center. So this is important, that these observations. And later people realized that these planets also also satisfy Kepler's laws. Later Newton also made observations of moons of Jupiter. Newton also made telescopes, and then It was very useful to make laws of physics. This is Isaac Newton. This is a famous quotation by Isaac Newton. If I have seen further, it is by standing on the shoulders of giants. എനിക്ക് കൂടുതൽ കാണാൻ കഴിച്ചിട്ടുണ്ടെങ്കിൽ അത് ഞാൻ ഈ ഭീമന്മാരുടെ തോളത്ത് നിന്നുകൊണ്ടാണ്. അവിടെ ജയൻസ് ഉദ്ദേശിക്കുന്നത് ഗലീലിയോ പോലെ ഉള്ളവരെയാണ്. So let me go over to Newton's contributions. This is the famous book by Newton called Principia. പഴയ പ്രൊനൗൺസിയേഷൻ പ്രിൻകിപ്പിയ ആണ്, ഇപ്പൊ പ്രിൻസിപ്പിയ എന്നാണ് നമ്മൾ പറയുക. This is Newton's own handwriting. The left side you see Newton's own handwriting. These are things made by Newton. I want to emphasize this because many people think Newton as a theoretician, but he was a very good experimentalist, very good observer. This is sundial built by Galileo when he was a school boy. And the right side you see a telescope, Newtonian telescope. Newton in the beginning made refractive telescopes, then he turned over to refraction telescopes, and these types of telescopes are known as Newtonian telescopes even today. And this is the first thing is interesting. This is called Newton's mountain. This is a drawing from Newton's book Principia. See, this is Earth, and think of a big mountain there, and you throw something to the right side with some speed, it will fall somewhere on Earth. You keep increasing this speed, and you'll reach a stage in which this will keep falling, but it will not reach Earth, it will go around Earth. So if you have a mountain of this height, and you throw something from there, it will go around Earth. And Newton said this is what happens in the case of moon. Moon going around Earth, he could explain this way. So he said the things falling down or particular motion, or even apple falling down, and moon going around Earth is all due to the same gravitational force. And he could even deduce that the gravitational law is gm/r². I will explain that later. Newton also did a lot of experiments with a pendulum. So this is a pair of pendula. You have one slightly bigger than the other, and he let them collide. So this is actually something like rigid body collisions. So what will happen if you have a heavier body and a lower body? They collide, both will move. Okay, and Newton realized that their speed actually can be estimated from the distance it travels after the collision. So from its amplitude, we can find the speed. For small amplitudes, the amplitude will be proportional to the speed of the ball. And if you have the mass also, they can definitely calculate the momentum. And from this, he realized that Newton's second law from analyzing collisions. And he also realized third law, that the force that A exerts on B is same on, if I call this F1 and this is F2. F1 is equal to minus F2. This also Newton realized. Then Newton tried to make use of these laws for explaining the celestial motions of planets around the sun. So let me very briefly explain how Newton arrived at this equation. According to Newton, there are some fundamental things that you have to think about. For example, I had mentioned the name of Descartes. He is known for Cartesian coordinates. You all know Cartesian coordinates. What is it? You have some axis x and y. You can even draw z axis. So if you have a particle, you can specify its x coordinates and y coordinates. And in 3 dimensions, you can specify x, y, and z. So that means we can have a mathematical description of things in the universe. If you specify its position by 3 numbers, then we can write down equations. Before Descartes, this kind of mathematical description was very, very difficult. You could only make qualitative statements. So Descartes' idea of coordinates was very useful for Newton, and these Cartesian equations were very useful. Descartes also founded what is now known as first law of motion, saying that if a body can be at rest, it can be moving at uniform speed. This follows from Galilean relativity itself. That is, in one frame of reference, it will be at rest, in another frame of reference, it will be moving with uniform speed. Then Galileo had also observed that things fall with the same acceleration. So then Newton realized that g is constant. That is, acceleration due to gravity is constant. That is, whether it is heavy body or a small body, it's same. But from Newton's second law, what is acceleration? Force is equal to mass into acceleration. So force by mass is acceleration. This is from the equation F equal to ma. So you have g equal to F by m. What does that mean? That would mean that F is proportional to mass. So if you have two bodies of mass m1 and m2, force experienced by this body will be proportional to m1. If it's a gravitational force, because the acceleration is same for all bodies, then force has to be proportional to m1. Similar argument will show that force experienced by mass m2 has to be proportional to m2. But these two forces should be equal and opposite. Force experienced by m1 and force experienced by m2 have to be equal and opposite. So you better have f proportional to m1, m2. Now, how did he think of one-way R-square law? Again, he had many arguments. For example, if you look at Kepler's laws, you from first law itself, you realize that it's planets move in elliptical orbit, and then Newton could deduce that elliptical orbits would imply one-way R-square law, because if it is elliptical orbit, there's an acceleration towards one of the foci, and only if it is of the from one-way R-square, you will get elliptical orbits. Another argument he had was with the falling apples and the moon. For example, apple will fall with g equal to 9.8 meter per second square. Now, if you look at moon, that's going around Earth in a nearly circular orbit, but in circular orbit there's an acceleration towards Earth, and that is much less than g. It is actually around g by 3,600. So acceleration of a moon towards Earth is 1 by 3,600 times that of a falling apple. And then Newton knew that distance of an apple from the center of Earth, if you compare with the distance that moon has from the center of Earth, there's a ratio of 60. ഞാൻ പറയുന്നത് ഇതാണ്, എർത്തിന്റെ റേഡിയസിന്റെ 60 ഇരട്ടിയാണ് മൂണിലേക്കുള്ള ഡിസ്റ്റൻസ്. അപ്പോൾ ഒരു ആപ്പിള് എർത്തിന്റെ സെന്ററിൽ നിന്ന് എത്ര ദൂരത്തിലാണോ അതിന്റെ 60 ഇരട്ടി ദൂരത്തിലാണ് മൂൺ. പക്ഷെ ആക്സിലേഷൻ 1 by 3,600 times അത്രയും കുറവാണ്. So that can be explained by one-way R-square law. That R you increase 60 times, then 1 by R-square is 1 by 3,600. From these arguments, he arrived at this equation, that is F equal to G m1 m2 by r square. And this was an exact law because there is no friction or any other force that you have to consider. If you take Earth and Sun, all other forces are negligible. You have to consider only gravitational force. Similarly, you can consider the gravitational force of Earth and Moon. Then people had many questions like, what about other stars? They will all attract our planet, but that forces are much, much, much less. And that also Newton made calculations. Let me go to next slide. So this was the Newton's formulation. Let me go further into other formulations. Newton's formulation, as I mentioned earlier, depended on the particular coordinate system, what is called a Descartesian coordinate system or Cartesian coordinate system. Later, people tried to apply this to all kinds of cases, and the people realized that it is better to go beyond the Cartesian coordinates. Then the idea of generalized coordinates came. Generalized coordinates. What are generalized coordinates? Coordinates that uniquely define the configuration of the system. So you should have enough coordinates and not more than that. For example, consider this case. What is this? This is what is called the Attwood's machine. Attwood's. So here were two masses, M1 and M2. M1 and M2 connected by a string going over a pulley, frictionless pulley, and the things will move. But these are not independent. These are connected by a string. So you say that is a constrained system. And if you know the coordinate of one, you know the other. So in generalized coordinate, you specify only one quantity. For this Attwood's machine, you need just one number to represent its position. Now think of this pendulum which moves in this direction. So you don't need x and y coordinates separately because these are not independent. X and y are fixed by the. If you fix x, y is automatically fixed because the length of the pendulum is fixed. So it's better to specify an angle. That is generalized coordinate. Now for a planetary motion, you could have used x and y coordinates, but it's better to use r and theta coordinates because gravitational force depends only on the distance. This is the idea of generalized coordinates, which is very useful, which was very useful concept. Now, Newton could not consider rigid bodies as such and describe its motion, but if you want to extend Newton's ideas to rigid bodies, like say this aeroplane, you need just six generalized coordinates. Three to represent its center of mass or any point, and another three as angles, Euler angles. There are three different motions possible: rotations, rolling motion, pitching, and yaw. Okay. For example, the picture itself explains, so I don't explain. So to discuss the motion of a aeroplane, assuming that the passengers are all fixed to the seats, you need just six coordinates. So this was the idea which is found very useful by Euler, and these are called Euler angles. And let me go over to something is called the principle of virtual work. For constraint system, this became a very useful idea. Idea of virtual displacement is the following. You think of two different configurations of the system, such that you don't all the constraints are strictly adhered to. You consider the constraints, but you don't consider the time dependence of constraint. So you consider the two different configurations at the same time and find the displacements. From this idea, people could get the principle of virtual work. That is a very useful idea because under static cases, force is all zero. All Fi means sum of all forces acting on the ith particle. Then the force is zero. then if f is 0, you can take that dot product with respect to virtual displacement sum over. If one of the term is 0, then you multiply and sum, so the whole thing will be 0. So delta W, this will be 0. Then this F, you divide into two things, applied forces and constrained forces. You think of a simple pendulum case. The pendulum is connected by a string. What is the force acting on a pendulum? There's of course gravity. If there was only gravity, pendulum bob will just simply fall down, but it's oscillating. That is because there are two forces acting on it. What are these forces? If you have pendulum in this form, you have gravitational force downwards, and then there's a tension. The sum of these two forces which moves it in this direction. So this force due to tension, you don't know the quantity of it. It is very difficult to calculate the quantity of tension. But you don't have to know it. You just say that this force consists of two times Fi applied and Fi constrained. That is, in this case, tension forces. You put this here and you have two summations. And now we consider the cases in which this second quantity is 0. That is work done by constraints is 0. This happens in the case of pendulum strings and things like that, because this string is itself by not doing any work, it doesn't have any energy. The string is not doing any energy. In Atwood's machine also, the string that goes off the pulley is doing no work. So in that case, you can write an expression like this. You drop the second time and you have just first time. Sum over I Fi at delta Ri equal to 0. This only the summation is 0 because you have dropped this time. Each of this is not 0. So this is called the principle of virtual work, and this idea of principal work, idea of virtual work can be used to explain various equations and various important identities. For example, you have this seesaw. You have one mass m1 here and another mass m2 here, and then you know the condition for equilibrium is m1 L1 plus equal to m2 L2. How do you get it? This you can derive from idea of principle, virtual work. You can try this as an exercise if you want. Now consider this, this body is fixed and you have a arrangement like this. This can move and here it can move. And can you find the relation between P and Q? Actually, this relation is Q equal to half P tan theta. This also you can calculate from the idea of virtual work, principle of virtual work. You can find this. These kind of equations are very useful in engineering and also in constraint statics. And this idea can be extended to actually cases in which there is a not equilibrium, there's forces acting. And there the idea is that you go to that frame of reference in which the particle is at rest and you again formulate the same thing, and you get the D'Alembert's principle. I'm not going to it for lack of time. So this is D'Alembert's principle. I will not go into details. You end up with this equation. This you might have studied, and this is very useful equation. And from this we can get what is called Lagrange's equations. Or by itself, you can deal with a lot of problems in which there are lots of constraints. Whether there is a force or not, this equation is always valid. So I will not go into details. Let me go to Lagrange's formulation. Lagrange lived after Newton. Lagrange extended Newton's ideas to coordinates which are not Cartesian coordinates, generalized coordinates. So I'll just give the highlights of Lagrange's formulation. One is that it uses generalized coordinates. So that's the one big advantage. It uses generalized coordinates. Then you can deal with the constraint systems. Then another advantage is that you deal only with the kinetic energy and potential energy. These are scalars, so you don't have to bother about vectors. Scalars have the advantage that you can add them with just numbers. So if you have a system with say 10 particles, you can add the kinetic energies of each particle and you can calculate the potential energy of the system. To get the total potential energy, you don't have to. You can add them just numbers. You don't have to bother that these are vectors. That's the advantage. And Lagrange's formulation can be extended to continuous systems. For example, liquids or gases, or even fields like electromagnetic field. Lagrange system can be extended, and can be extended to relativity systems also. That is very useful when Einstein developed his theory of relativity, and that Lagrange's formulation you could easily extend to relative systems. And it also comes in quantum mechanics. I will not go into detail, but just mention that the quantum mechanics also can be expressed in terms of Lagrange's formulation of quantum mechanics. Lagrange equation, one famous derivation is by using axiom principle. Let me explain that. Its beginning is in the Fermat's principle of least time. This is Fermat. Though the spelling is Fermat, is a French not really a scientist. He was actually a lawyer, but he is known as a scientist. He did a lot of interesting work in physics and mathematics. And around 1660, he formulated Fermat's principle, which says that light goes from one place to another place, such that it goes through the shortest path, shortest time. So even if you have a mirror, it will reflect in such a way that if you have to reach from A to B, if there are different possibilities, it will go in such a way that the time is least. From this, we can find the roots of reflection. And even for refraction, if you consider all kinds of paths from A to B, this is in air and this is in glass. So you have two different media. In this case, you can consider all kinds of paths from A to B, like this and this. You can think of straight lines. But in glass, it will move slower than in air. So if you allow all kinds of paths, it will choose the path in such a way that the time taken is least. So when Fermat formulated this idea, it looked very strange. It's as if light thinks of all kinds of paths and make a calculation and goes through the path such that the time taken is the least. But this was later explained by Huygens theory of wavelets. You might have studied in plus 2. So Fermat's equation could be explained by Huygens, and Huygens' expression is found more reasonable than Fermat. But anyway, we mentioned Fermat's theory was first. It was kind of a principle of this time, and that gave people motivation to develop a principle of least action for classical mechanics. So this is another interesting problem called the Brachistochrone problem. The question was this: a ball is allowed to go from point A to B through a frictionless path. All kinds of paths are allowed. Which path will take it to from A to B in least time? You might think that straight line is okay, but it's not okay. Straight line will take more time than all of the other paths. So this was a great problem posed by Bernoulli, and many great mathematicians solved it. One of them was Isaac Newton, and the solution turns out to be cycloid, this path. So this also helped in developing calculus of variations. This is a person called Maupertuis. He was the first person to propose a principle of least action. He said that particles or materials move in such a way that this integral, P dot dq. P dot dq means if you have n particles, P1 dq1, P2 dq2, etc. P is momentum and Q is position coordinate. He didn't call it momentum. He just said you take mass and then velocity and multiply. He didn't call it the name momentum. And he said that if energy is fixed, so he has condition that E is constant. If energy is fixed, then particle move such a way that this quantity W is minimum. This is now known as Maupertuis principle of least action. Let me go to next slide. This is another interesting thing. This is a chain. Now, can you find what is the shape of this curve? Or you have a chain like this. The shape of the curve is actually a catenary. And it's a very interesting problem. You can see in the textbooks. This is a catenary. Catenary actually means chain. So this is given by cos hyperbolic function. This was another interesting problem that led to Kalpasa variations. So action principle you state as delta is equal to 0, where S is action defined as integral of L over T, and L is actually kinetic energy minus potential energy. And here the best statement is to say that it's a principle of stationary action. This is not necessarily minimum, but this condition says that delta is equal to 0 says that if you make a small variation in the actual trajectory, delta S will be 0. That S will not change, it will remain stationary to first order. And that will give the real trajectories materials. The great advantage of this principle is that this has applicability everywhere. This you can use for fields, this you can use for continuous systems, this can be written for relativist systems, all kinds of systems you can use this principle. And when they formulated, nobody had any idea of from where this equation comes. This considers a fundamental principle, and from this you can get everything in classical mechanics. Everything in classical mechanics, all the laws of classical physics, all the basic laws you can get from this principle. But interestingly, people realize later that this principle of stationary action actually has its origin in quantum mechanics. That I will not go into details. See, for example, principle of stationary action. You take electromagnetic field. This F square stands for F mu nu, F b nu. Sorry, F mu nu. This is for not just for this, and J dot A means J mu A mu. I am using shorter notations. So this is the action for electromagnetic fields. This J stands for currents, and the F mu nu stands for electromagnetic tensor constructed out of electric and magnetic fields. So F is just a matrix constructed from electric field and magnetic fields. And you take this equation delta is equal to 0. From this you can get all these 4 equations you get from this. So if you just put this action, very simple action, and put delta is equal to 0, you'll get all of these Maxwell's equations. And you know very well that given the Maxwell's equation, you can get all other laws like Coulomb's law, Gauss's law, Ampere's law, Faraday's law. All these law you can get from all of classical electrodynamics. You can get from Maxwell's equations and Lorentz force law. That is contained in this action. So it's a great unification, because Maxwell's equation represents all of electrical phenomena, all of magnetic phenomena, and all of electromagnetism. That's theory of light. All classical theories of electricity, magnetism, and optics you get from this Maxwell's equation, and then it comes from principle of stationary action with this action. You can even make a quantum theory of this, and still it will explain all the classical and the quantum phenomena associated with electricity, magnetism, and optics. And that's what I have written in the first case. This is called quantum electrodynamics Lagrange. The second time is same. This is the interaction of charged particles with the matter. You will learn about it later. And the second thing I have written is called the Einstein-Hilbert action. This is action for gravitation according to general theory of relativity. Yes, sum means for all the matter in the universe, we can action here, and this is for the gravitational fields. And then you put delta is equal to 0, and then you will get this equation. This is called the Einstein's equation, and this equation explains how our universe expands, how black holes exist, and all such things we can explain with this law. And that also comes from the equation delta is equal to 0. So I want to emphasize that this is very, very fundamental law of classical physics. So far I was talking about Lagrange's formulation, then we have Hamilton's formulation. I will not go into details because I have already taken the class for 1 hour. So Hamilton's approach, this you go from Lagrangian to Hamiltonian by what's called a legendary transformation given this way. P q dot minus L, and L is a function of coordinates and velocities. Hamiltonian will be a function of coordinates and momenta. And Q stands for coordinate, P stands for momenta, and you get you write these equations, which is called the Hamilton's equations or canonical equations. Hamilton's method has several advantages over Lagrange's method. For example, in Lagrange's method, you take generalized coordinates. Here you have generalized coordinates and momenta, and you can have transformations between them. What somebody calls momentum, you can call coordinate and other ways. So you can have a transformation from Q's and P's to capital Q and capital P. All kinds of transformations are called canonical transformations. So that gives a lot of freedom. You can even make a transformation such that the new Hamiltonian is 0, and then you get what is called Hamilton-Jacobi equations that you can use to explain wave nature and the particle nature of light. Ray optics and wave optics can be combined using Hamilton's formalism. And Hamilton's formalism was very handy for people who developed quantum mechanics, because when you learn about quantum mechanics, whether you write Schrodinger equations or Heisenberg equations, Hamilton has an important role. Also, when you consider statistical mechanics, Hamilton plays a very important role. So this Hamilton's formulation also plays an important role in the foundations of classical mechanics. With this, I will stop because I have already taken around 1 hour. So let me come back. Hello. Can you hear me? Now it's time for questions if you have.
Thank you,
Please.
sir. And now,
കേൾക്കാമോ? Okay.
yes, sir. And now
കുട്ടികൾക്ക്
we are
ആരെങ്കിലും
moving
ചോദ്യം
on
ഉണ്ടെങ്കിൽ ചോദിക്കാം,
to yes, interaction
അല്ലെങ്കിൽ
session.
കമന്റ്സ്
I
ഉണ്ടെങ്കിൽ പറയാം,
welcome
അല്ലെങ്കിൽ
each
ഞാൻ പറഞ്ഞത് ക്ലാരിറ്റി കുറവുണ്ടെങ്കിൽ പറയാം.
Yes, sir. So let's start off with the discussion. I invite all the participants to join this session.
നിങ്ങൾക്ക് അൺമ്യൂട്ട് ചെയ്ത് ഡയറക്റ്റ് വേണമെങ്കിൽ സാറിനോട് ചോദിക്കാം കേട്ടോ. ചാറ്റ് ചെയ്യാൻ ചാറ്റിൽ ഇടണമെന്നില്ല കേട്ടോ.
ചാറ്റ് ഉണ്ടോ ഇവിടെ? കാണാൻ എവിടെയാണ് ചാറ്റ്? ഓക്കെ, കാണുന്നുണ്ട്. നോട്ടെ, ചാറ്റിലൊന്നും ഇല്ലല്ലോ. ഉണ്ടോ? ഒന്നും കാണുന്നില്ല.
ഇല്ല.
ഞാൻ പറയുന്നതൊക്കെ വ്യക്തമായിട്ട് കേൾക്കാമായിരുന്നോ?
എല്ലാം കേൾക്കാം സാറേ, കേൾക്കാം. എനിക്ക് തോന്നുന്നത് അവർക്ക് ഈ ഇത് അൺമ്യൂട്ട് ചെയ്ത് ചെയ്യാനുള്ള ഇതായിരിക്കാം ഒരു പക്ഷേ.
നിങ്ങൾ പെർമിഷൻ കൊടുത്തിട്ടുണ്ടാവില്ല അല്ലേ?
അത് കൊടുത്ത് നിങ്ങൾക്ക് അൺമ്യൂട്ട് ചെയ്തിട്ട് സംസാരിക്കാം കേട്ടോ, ചാറ്റിൽ ഇടണമെന്നില്ല. Permission.
ഒരു ക്വസ്റ്റ്യൻ കാണുന്നുണ്ട്. Can you explain brachistochrone problem? കേൾക്കാമോ ഞാൻ പറയുന്നത്?
കേൾക്കാം സർ, കേൾക്കാം.
അപ്പോൾ ഞാൻ ആ ക്വസ്റ്റ്യൻ ആൻസർ ചെയ്യാം.
ഓക്കെ.
ഞാൻ ആ സ്ക്രീൻ എടുക്കുകയാണെങ്കിൽ വരാമെന്ന് തോന്നുന്നു. ഓക്കെ, ബ്രാക്കിസ്റ്റോക്രോൺ പ്രോബ്ലം ഇതാണ്. സ്ക്രീൻ കാണാമോ? ഞാൻ ഷെയർ ചെയ്യേണ്ടി വരും അല്ലേ? ഒരു സെക്കൻഡ് ഷെയർ ചെയ്ത ഒരു സെക്കൻഡ്. സ്ക്രീൻ കാണാമോ?
കാണാം സർ. ഇപ്പോ ഓക്കെ, കാണാം സർ.
You have point A and you have point B. ഇതിലൂടെ ഒരു ഫൈൻഡ് എ പാത്ത് അല്ലെങ്കിൽ ഒരു സർഫസ് കൊടുക്കുകയാണെങ്കിൽ അതിലൂടെ ലീസ്റ്റ് ടൈമിൽ എത്ര ഏതായിരിക്കും എന്നാണ് ക്വസ്റ്റ്യൻ. സപ്പോസ് യു ഹാവ് എ ഡിഫറെന്റ് പാസ് അലൗഡ്. അത് ബോൾ റോൾ ചെയ്യുകയാണെങ്കിൽ ലീസ്റ്റ് ടൈം കൊണ്ട് എയിൽ നിന്ന് ബിയിലേക്ക് എത്തുന്ന എവിടെയാണെന്നുള്ളതാണ് ബ്രാക്കിസ്റ്റോക്രോൺ പ്രോബ്ലം. ബ്രാക്കിസ്റ്റോക്രോൺ എന്ന് പറഞ്ഞാൽ അതിന്റെ അർത്ഥം ക്രോൺ എന്ന് വെച്ചാൽ ടൈമാണ്, ബ്രാക്കിസ്റ്റോസ് എന്ന് പറഞ്ഞാൽ ലീസ്റ്റ് ടൈം, ലീസ്റ്റ്. അപ്പോൾ രണ്ട് ചേർന്ന ബ്രാക്കിസ്റ്റോക്രോൺ എന്ന് പറയാം. അത് ബെർണോളി എന്ന് പറഞ്ഞ ആളാണ് പ്രപ്പോസ് ചെയ്തത്. അത് അതിന്റെ വലിയൊരു സമ്മാനം ഒക്കെ അനൗൺസ് ചെയ്തു. എന്നിട്ട് 6 മാസം സമയം കൊടുത്തു. എന്നിട്ട് ഫേമസ് ആയിട്ടുള്ള കുറച്ച് മാത്തമാറ്റീഷ്യൻസ് സോൾവ് ചെയ്തു. അപ്പോൾ ആ സമയത്ത് ന്യൂട്ടൺ ജീവിച്ചിരിക്കുന്നുണ്ടായിരുന്നു. അപ്പൊ ന്യൂട്ടൺ ഇത് ആദ്യം അറിഞ്ഞില്ലായിരുന്നു. അപ്പോൾ ഐസക് ന്യൂട്ടന് ഇതൊരു കോപ്പി അയച്ചു കൊടുത്തു ഈ പ്രോബ്ലം. അപ്പോ ന്യൂട്ടൺ അന്ന് നല്ല പ്രായമുള്ള ആളായിരുന്നു. ഫെല്ലോ ഓഫ് റോയൽ സൊസൈറ്റിയുടെ പ്രസിഡന്റും ഒക്കെ ആയിരുന്ന സമയത്താണ് ഈ പ്രോബ്ലം ഒരു ദിവസം വൈകുന്നേരം 4 മണിക്ക് ന്യൂട്ടന്റെ കയ്യിൽ കിട്ടുന്നത്. മറ്റു പലരും 6 മാസം കൊണ്ട് സോൾവ് ചെയ്യാൻ പറ്റാതിരുന്നതും ചിലർ സോൾവ് ചെയ്തതാണ്. കുറച്ച് പേര് മാത്രം സോൾവ് ചെയ്തിരുന്നു. ന്യൂട്ടൺ ആ 4 മണിക്ക് കിട്ടിയപ്പോൾ ആ പ്രോബ്ലം ആയിട്ടിരുന്നു. തുടർച്ചയായിട്ട് 12 മണിക്കൂർ ന്യൂട്ടൺ വർക്ക് ചെയ്തു. വൈകുന്നേരം 4 മണി മുതൽ രാവിലെ 4 മണി വരെ അത് വർക്ക് ചെയ്ത് സോൾവ് ചെയ്ത് സൊല്യൂഷൻ അയച്ചു കൊടുത്തു. അയച്ചു കൊടുത്തപ്പോൾ ന്യൂട്ടന്റെ പേരൊന്നും വെച്ചില്ല. അത് അനോണിമസ് ആയിട്ടാണ് അയച്ചു കൊടുത്തത്. അവസാനം ബെർണോളിയുടെ അടുത്തെത്തിയപ്പോൾ അദ്ദേഹം അത് പ്രസിദ്ധീകരിച്ചു മറ്റുള്ളവരുടെ പ്രൂഫിന്റെ ഒപ്പം. ന്യൂട്ടൺ വളരെ എലിഗന്റ് ആയിരുന്നു. അപ്പൊ ന്യൂട്ടന്റെ സ്റ്റേറ്റ്മെന്റ്സിൽ നിന്ന് ന്യൂട്ടൺ പേരെഴുതിയിട്ടില്ലെങ്കിലും ന്യൂട്ടൺ ആയിരിക്കും അത് കണ്ടുപിടിച്ചെന്നുള്ളത് അയാൾ ഗസ് ചെയ്തു. എന്നൊരു ഫേമസ് സ്റ്റേറ്റ്മെന്റ് അയാൾ പറഞ്ഞു, ദ ലയൺ ഈസ് റിവീൽഡ് ബൈ ഇറ്റ്സ് പോസ്. ഒരു സിംഹത്തിന്റെ നഖപ്പാടുകൾ എനിക്ക് പ്രൂഫിൽ കാണാൻ പറ്റുന്നുണ്ടെന്ന് ബെർണോളി പറഞ്ഞു. അപ്പൊ ഇതിന്റെ പ്രൂഫ് നെഗ്രേജ് ഇക്വേഷൻ വെച്ചത് ചെയ്യാൻ പറ്റും. അതൊരു പ്രോബ്ലം ആയിട്ട് കൺവേർട്ട് ചെയ്യാം. അതുപോലെ സിമിലർ ഇക്വേഷൻ ആയിട്ട് കൺവേർട്ട് ചെയ്തിട്ട് ചെയ്യാൻ പറ്റും. അപ്പോ സൈക്ലോയിഡ് ആയിട്ടാണ് ഇതിന്റെ സൊല്യൂഷൻ. ഞാൻ ഒരു ചെറിയ വീഡിയോ ആയിട്ട് അത് ഷെയർ ചെയ്യാൻ പറ്റുമോ നോക്കട്ടെ കേട്ടോ. ഒരു സെക്കൻഡ്, അറിയാർ പെർമിഷൻ. അപ്പൊ ഞാൻ ഐ വിൽ നോട്ട് ട്രൈ വീഡിയോ. ഇത് നിങ്ങൾക്ക് ബ്രാക്കിസ്റ്റോക്രോൺ പ്രോബ്ലം നെറ്റിലേക്ക് അടിച്ചു പോയി കഴിഞ്ഞാൽ വീഡിയോസ് കിട്ടും. പല സ്ഥലത്ത് ഇത് ഡ്രോപ്പ് ചെയ്തിട്ട് താഴേക്ക് വീഴുന്നത്. അപ്പൊ ഇതിന്റെ കാരണം ഇത് സൊല്യൂഷൻ ഒരു ക്വാളിറ്റി എക്സ്പ്രഷൻ പറയാം. തുടങ്ങുമ്പോൾ മാക്സിമം ആക്സിലേഷൻ കൊടുക്കുകയാണ് നല്ലത്. സോ ബ്രാക്കിസ്റ്റോക്രോൺ തുടങ്ങുമ്പോൾ ഇനിഷ്യലി ഡയറക്റ്റ് ആക്സിലേഷൻ ടുവേർഡ്സ് ഡൗൺവേർഡ്സ്. അപ്പൊ കർവ് തുടങ്ങുന്നത് ഇങ്ങനെയായിരിക്കും, വെർട്ടിക്കൽ ആയിട്ടാണ് തുടങ്ങുക. എന്നിട്ട് പിന്നെ അത് സ്മൂത്ത് ആയിട്ട് ഞാൻ വരയ്ക്കുമ്പോൾ ശരിയാവില്ല അതിനകത്ത് ഇങ്ങനെ ഉള്ളത് ഇങ്ങോട്ട് എത്തും. ഇങ്ങനെയാണ് ബ്രാക്കറ്റ് കൊണ്ടുള്ള വരിക. അപ്പോൾ ഫാൾ ചെയ്യുന്ന സമയത്ത് ഡയറക്റ്റ്ലി ഡൗൺ ബേഡ്സ്. സോ വിൽ ഗെറ്റ് മാക്സിമം ആക്സിലറേഷൻ ഇൻ ദ ബിഗിനിങ്. പിന്നെ ഇത് ബിയിലേക്ക് എത്തിക്കാൻ വേണ്ടിയിട്ട് ചരിച്ചു കൊണ്ടുവരിക. അപ്പോൾ അതാണ് ഐഡിയ. തുടങ്ങുമ്പോൾ തന്നെ നല്ല ആക്സിലറേറ്റ് കിട്ടി കഴിഞ്ഞാൽ ആവറേജ് സ്പീഡ് കൂടുതലായിരിക്കും. നേരെ സ്റ്റൈലിൽ വരയ്ക്കുന്നേക്കാളും നല്ലത് അതാണ്. അതാണ് അതിനെക്കുറിച്ച് എനിക്ക് പറയാനുള്ളത്. എനിക്കിതിൽ വരച്ചുണ്ടാക്കാൻ ബുദ്ധിമുട്ടുണ്ട്. വീഡിയോ വേണമെങ്കിൽ നിങ്ങൾക്ക് കിട്ടുന്ന ഞാൻ ഷെയർ ചെയ്ത് തരാം. ഇതിനകത്ത് നിങ്ങളുടെ ആപ്പ് വെച്ച് എങ്ങനെ ഷെയർ ചെയ്യണമെന്ന് എനിക്ക് സംശയമുണ്ട്. ഓക്കെ, ഇനി അടുത്ത ക്വസ്റ്റ്യൻ എന്താണെന്ന് നോക്കാം. How do you say that variation in action remains zero even though there is variation in generalized coordinates taken?
Okay.
ഓക്കെ, അത് ഞാൻ ആ സ്ക്രീൻ വെച്ചത് എക്സ്പ്ലെയിൻ ചെയ്യായിരിക്കും നല്ലത്.
Okay, sir.
ഓക്കെ, ഒരു സ്ക്രീൻ കാണുന്നുണ്ടല്ലോ അല്ലേ?
Sir.
For example, assume that S Q is something like this and S is something like this. Okay. Now you vary Q here at the minimum, then delta S will be 0. In this case, ds by dq will be 0 at minimum. So at this point, though you vary Q, Q goes to Q plus delta Q, S goes to S plus delta S. Around a minimum, or if you have a maximum, point okay. At these points and these points, delta is 0 or ds by dq will be 0 at minimum and maximum. So function ingane povaanengil minimum maximum okay, delta is 0 ആയിരിക്കും. ചോദിച്ചാൽ മനസ്സിലായെന്ന് വിചാരിക്കണം. ഫസ്റ്റ് ഡെറിവേറ്റീവ് 0 ആയി കഴിഞ്ഞാൽ അപ്പൊ അതിന്റെ അർത്ഥം എന്താണ്? ഇപ്പൊ dy by dx 0 ആണെന്ന് അർത്ഥം എന്താണ്? dx 0 അല്ല, പക്ഷെ dy 0 ആണ്. ദാറ്റ് എക്സിൽ ചെറിയ വേരിയേഷൻ വരുത്തിയാലും വൈയിൽ വേരിയേഷൻ വരുന്നില്ല. അത് ഫോർ എക്സാമ്പിൾ കോൺസ്റ്റൻസ് അത് സംഭവിക്കും, അല്ലെങ്കിൽ ഒരു മിനിമത്തിലോ മാക്സിമത്തിലാണെങ്കിലും ഇത് സംഭവിക്കും. ഇതാണ് ഞാൻ പറയാൻ ഉദ്ദേശിച്ച പോയിന്റ്. അതാണ് കൺവിൻസിംഗ് ആണ് വിചാരിക്കുന്നത്.
Is there any questions? ഇനിയുണ്ടോ? Mekha. Okay.
Okay, thank you, ma'am, and thank you, sir. Moving on. Now, Dr. Andrews Abraham, who has got the heart of students within her short period of mentoring at our college, I invite ma'am, our joint coordinator, to deliver the vote of thanks. Welcome, ma'am.
Good evening, everyone. It's my pleasure to mark the end of such a beautiful gathering with a vote of thanks. It's a great honor for me to be given the opportunity to propose the vote of thanks on this special day. First of all, I would like to thank Almighty God for making today's event a grand success. Today's webinar was full of knowledge and interesting concepts on classical and quantum phenomena. It gave us deep insights into the field of classical mechanics and also revealed some interesting aspects on Maxwell's equations and many other equations. On behalf of the college management, the Department of Physics, and everyone present online, I would like to extend my heartiest thanks to our Honorable Speaker, Professor M. Shaji, sir, for enlightening us with his vast knowledge. Thank you, sir.
Thank you.
Thanks.
Wholeheartedly, I thank our principal, Father Prashant Palakapillil, the soul and blood of the Hashim family, for the valuable support and encouragement for organizing such an event. Thank you, Reverend Father Principal. We have been fortunate enough to get the support and guidance of our captain, the head of our department, Professor C.B. Matthewson. Thank you, sir, for your evergreen support, which has made this function a memorable one for all of us. The program would not be possible without the relentless hard work and efforts of the coordinator of this event, Professor Navya SN, through which we could attend to such an eminent personality and also which has attracted participants from colleges all over India. Thank you, ma'am, for your hard work and sincere efforts for the successful conduct of this event for the benefit of the students. My sincere thanks to the organizing committee and all faculties of the Department of Physics for all support and suggestion for the benefit of the program. I congratulate and thank all of you for your valuable, attentive and active participation which has made this event a successful one. I must not forget to thank the library staff and the organizing team for the smooth conduct of the program through WebEx platform. The special thanks to the student committee for working closely to mark this function with success. Once again, thank you everyone for making it a great success. Have a good day. Thank you.
Thank you, ma'am.
Thank you.
Once again,
Thank
once
you,
again, we
Shadi
would like to
sir.
thank from the bottom of
Thank you.
Special thanks to the department and secretariats. Thanks to all other participants. സാർ ഇപ്പൊ തിരുവനന്തപുരത്താണോ ഇവിടെ ഉണ്ടോ സ്ഥലത്തുണ്ടോ?
ഞാനിപ്പോ കുസാറ്റിലുണ്ട്.
കുസാറ്റിലുണ്ടല്ലോ. ശരി ശരി. ഓക്കെ.
ഓക്കെ, ശരി സാറേ.
ശരി സാറേ, താങ്ക് യു.
ഓക്കെ, ഞാൻ കിട്ടിയാണേ.
ആ ശരി, ആയിക്കോട്ടെ.
ഹലോ.
Once again, from the PG students of Sacred Heart College, we would like to thank from the bottom of our hearts each and every one. A special thanks to our speaker of the day who has already left this meeting, but it was really a thought-provoking session. And our dear Navya ma'am was very sure that her students must attend such a session because she used to say that her sir used to take classes in a way more, always more provoking to thoughts and discussions. It was really an interactive session if it would have been taken a much more time. And I'd like to thank our HOD, Dr. C.B. Matthew sir, and all other teachers of our department. Thank you. Thank you all. And thank you participants for your active participation.
Thank you, Megha. Thank you, Megha, for your wonderful comparing. Okay.
Thank you. Thank you.
The meeting
You
is
can let the meeting.
okay. Okay. Over.